And the interesting thing that happens here is that we switch signs inside the absolute value. Instead of taking an absolute value of negative, you're now taking the absolute value as a plus point of a positive. And that's why you see a switching direction here of this line. And so you see the same thing happening right here. So this point, right over here, we know that our function, we know that our equation is to evaluate out to 0. And this is where it's going to switch signs. And so we say, okay, well, this looks like an absolute value. So it's going to have before y is equal to the absolute value of something. And so we say, okay, how do I, if x is 3, how do I make that equal to 0? Well, I can subtract 3 from it. If I say y is equal to the absolute value of x minus 3, well, let's try it out. Let's see if it makes sense. So when x is equal to 3 minus 3 is 0. Absolute value of that is 0. That works out. When x is equal to 4 minus 3 is 1. Absolute value of 1 is indeed 1. And if x is equal to 2, well, 2 minus 3 is negative 1. The absolute value of that is 1. So once again, I'm showing you this by really trying out numbers, trying to give you a little bit of intuition, because that wasn't obvious to me when I first learned this. But if I'm shifting to the right, which it looks like I'm increasing an exponent, then what I would really do is replace my x with an x minus the amount that I'm shifting to the right. But I encourage you to try numbers and think about what's happening here. At this vertex right over here, whatever was in the absolute value sign was equaling 0. It's when whatever was in the absolute value sign is switching from negative signs to positive signs. So once again, if you shift 3 to the right, that has to happen at x equals 3. So whatever is inside the absolute value sign has to be equal to 0 at x equals 3. And this, pause this video and really think about this. It isn't making sense. And even as you get more and more familiar with this, I encourage you to try out the numbers. That will give you more, it's not just memorize. Yeah, if I shift to the right, replace x with x minus the amount that I shift, I always try the numbers and try to get an intuition for that works. But now, let's start from here and shift 4 up. And shifting 4 up is, in some ways, a lot more intuitive. So let me do that. Let me shift 4 up. Next, let me move. I'm going to go up 1, 2, 3, and 4. Right? So now I've shifted 4 up. And this is a reminder of what we've even done. The first part, we shifted 3 to the right, and now we are shifting 4 up. So now we are shifting 4 up. So before y equals 0, but now y needs to be equal to 4. So whatever this was evaluated to, we now have to add 4 to it. So when we just shifted 3 to the right, our equation was y is equal to the absolute value of x minus 3. But now whatever we were getting before, we now have to add 4 to it. We're going up in the vertical direction. So we just have to add 4. Now this makes a little bit more sense. If we're shifting in the vertical direction, if you shift up in the vertical direction, well, you just add a constant by the amount you're shifting. If you shift down in the vertical direction, well, you would subtract. If you said shift down 4, you'd subtract 4 right here. The less intuitive thing is what we do with x. When you shift to the right, you actually replace your x with x minus the amount that you shifted. Once again, try out numbers until it really makes some intuitive sense. But this is what we would finally get. The equation of this thing right over here is y is equal to the absolute value of x minus 3 plus 4. the graph of y is equal to absolute value. X is reflected across the x-axis and then scaled vertically by a factor of 7. What is the equation of the new graph? So pause the video and see if you can figure that out. All right, let's work through it together now. Now, you might not need to draw it visually, but I will, just so that we can all together visualize what is going on. Let's say that's my x-axis, and that is my y-axis. Y equals the absolute value of x. So for non-negative values of x, y is going to be equal to x. Absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. So it's going to look like this. It's going to have a slope of 1. And then for negative values, when you take the absolute value, you're going to take the opposite. You're going to get the positive. So it's going to look like this. Let me see if I can draw that a little bit cleaner. This is a hand-drawn sketch, so bear with me. But hopefully this is familiar. You've seen the graph of y is equal to absolute value of x before. Now let's think about the different transformations. So first they say, is reflected across the x-axis. So for example, if I have some x value right over here, before I would take the absolute value of x and I would end up there. But now we want to reflect across the x-axis. So we want to essentially get the negative of that value associated with that corresponding x. And so, for example, this x, before we would get the absolute value of x, but now we want to flip across the x-axis and we want to get the negative of it. So in general, what we are doing is we are getting the negative of the absolute value of x. In general, if you're flipping over the x-axis, you're getting the negative. You're scaling the expression or the function by a negative. So this is going to be y is equal to the negative of the absolute value of x. Once again, whatever absolute value of x was given you before for a given x, we now want to get the negative of it. We now want to get the negative of it. So that's what reflecting across the x-axis does for us. But then they say scaled vertically by a factor of 7. And the way I view that is if you're scaling it vertically by a factor of 7, whatever y value you got for a given x, you now want to get 7 times the y value. 7 times the y value for a given x. And so if you think about that algebraically, well, if I want 7 times the y value, I'd have to multiply this thing by 7. So I would get y is equal to -7 times the absolute value of x. And that's essentially what they're asking. What is the equation of the new graph? And so that's what it would be. The negative flips us over the x-axis, and then the 7 scales vertically by a factor of 7. But just to understand what this would look like, well, you multiply 0 times 7, it doesn't change anything. But whatever x this is, this was equal to negative x, but now we're going to get to negative 7x. So let's see, 2, 3, 4, 5, 6, 7. So put something around that. So our graph is now going to look like this. It's going to be stretched along the vertical axis. If we were scaling vertically by something that had an absolute value less than 1, then it would make the graph less tall. It would make it look wider. It would make it at least look a little bit more symmetric. So it's going to look something like that. But the key issue, and the reason why I'm drawing is so you can see that it looks like it's being scaled vertically. It's being stretched in the vertical direction by a factor of 7. And the way we do that algebraically is we multiply by 7. And the negative here is what flipped us over the x-axis. Function g can be thought of as a stretched or compressed version of f of x is equal to the absolute value of x. What is the equation for g of x? So you can see f of x is equal to the absolute value of x here in blue. And then g of x, not only does it look stretched or compressed, but it also is flipped over the x-axis. So like always, pause this video and see if you can come up yourself with the equation for g of x. All right, now let's work through this together. So there's a couple of ways we could do it. We could first try to flip f of x and then try to stretch or compress it, or we could stretch or compress it first and then try to flip it. let's flip it first. So let's say that we have a function that looks like this. It's just exactly what f of x is, but flipped over the x-axis. So it's just flipped over the x-axis. So all the values for any given x, whatever y you used to get, you're now getting the negative of that. So this graph right over here, this would be the graph. I'll call this y is equal to the negative absolute value of x. Whatever the absolute value of x would have gotten you before, you're now going to get the negative, or the opposite of it. So this is getting us closer to our definition of g of x. The key here is, how do we appropriately stretch or squeeze this green function? So let's think about what's happening. On this green function, when x is equal to 1, the function itself is equal to negative 1. But we want it, if we want it to be the same as g, we want it to be equal to negative 4. So it's actually 4 times the value. For given x, at least for x equals 1, g is giving me something 4 times the value that my green function is giving. That's not just true for positive x's, it's also true for negative x's. You can see it right over here. When x is equal to negative 1, my green function gives me negative 1, but g gives me negative 4. So it's giving me 4 times the value. It's giving me 4 times the negative value, so it's going even more negative. So what you can see, to go from the green to g, you have to multiply this thing right over here by 4. So that is what essentially stretches it down in the vertical direction. So we could say that g of x is equal to, it's not negative absolute value of x, negative 4 times the absolute value of x. And you could have done it the other way. You could have said, hey, let's first stretch or compress f. You say, all right, before we even flip it over, if we were to unflip g, it would look like this. If we were to unflip g, it would look like this. If we were to unflip g. So this thing right over here, this thing looks like 4 times f of x. We could write this as y is equal to 4 times f of x. Or you could say y is equal to 4 times the absolute value of x. And then we have a negative sign. Whatever positive value we're getting before, you now get the opposite value. And that would flip it over and get you a g, which is exactly what we already got. Draw that. It's going to look like that right over there. So whereas to graph f of x is equal to 2 times the absolute value of x plus 3 plus 2. And what they've already graphed for us, this right over here, this is the graph of y is equal to the absolute value of x. So let's do this through a series of transformations. So the next thing I want to graph, let's see if we can graph y is equal to the absolute value of x plus 3. Now, in previous videos, we have talked about it. If you replace your x with an x plus 3, this is going to shift your graph to the left by 3. You could view this as the same thing as y is equal to the absolute value of x minus negative 3. Whatever you are subtracting from this x, that is how much you are shifting it. So you're going to shift it 3 to the left. And we're going to do that right now. And then we're just going to confirm that it matches up, that it makes sense. So let's first graph that. Get my ruler tool here. So if we shift 3 to the left, it's going to look something like this. So on that, when whatever we have inside the absolute value sign is positive, we're going to get essentially this slope of 1. And whenever we have inside the absolute value sign is negative, we're going to have a slope of essentially -1. So it's going to look like that. Now let's confirm whether this actually makes sense. Below x equals -3, for x values less than -3, what we're going to have here is this inside of the absolute value sign is going to be negative, and so then we're going to take its opposite value, and so that makes sense. That's why you have this downward line right over here. Now for x is Than x, which is less than or equal to, by now we're used to seeing functions defined like h of y is equal to y squared, or f of x is equal to the square root of x. What we're now going to explore is functions that are defined piece by piece over different intervals, and functions like this are, you'll sometimes view them as a piecewise, or these types of function definitions, they might be called a piecewise function definition. And so let's take a look at this graph right over here. This graph, you can see that the function is constant over this interval for